Well, this is not a serious class. It's just an introduction of the VLSI processes. And as I mentioned in the introduction of this class last time, it consists of 8 chapters. It begins with the single crystal growing, chapter 1, and then diffusion, oxidation, ion implantation, chemical vapor deposition, dry etching, and lithography and metallization. Okay, and for each unit processes, I try to cover the basic theories behind the practical processes, and then we're going to introduce the practical processes related to each chapter. Okay. So this is a first class, so I like to talk about what is the VLSI first. VLSI, very large scale integration. Did you put in? Okay. You can see. Do you think you can focus on this? VLSI, very large scale integration. This is basically an integration of transistors. Integration of transistors, okay? And they had to be integrated separately, electrically separated, and then that has to be connected to make a circuit, okay? So for the integration, we need to collect all the transistors in one place, electrically separated, isolated. And then we have to find a way to make a connection of these transistors to make a circuit. Okay? These two things has to be done to do the integration. So basically what we are going to discuss in this class is related to the all processes to form transistors in one place, electrically isolated each other, and then later part of this VLSI processes, we are going to discuss about the connection of those transistors, which has been integrated in one place, electrically isolated. Okay, and of course it started out with the small scale integration and a middle scale integration and large scale integration. Now we are in the era of very large scale integration, and that is related to the number of transistors collected in one place. And before we, this is the wafer, and each one is the die, and all these dies are the same, okay? And in each die, the size of each die is about 1 to 1 centimeter, 1 by 1, or 1 by 2 centimeter of that size, okay? And then, can I move this thing? How can I move? Before the solid state transistor, we used to use a vacuum tube for the active elements of the electronic circuits. basically we have a 4 element, which is a resistor, inductor, and resistor, inductor, and a capacitor, and a transistor. Okay. These are the 4 elements of the electronic circuits, and this transistor is going to be called the active element. These 3 parts are called passive elements because it just change the signal. But this active element, it is amplifying the signals. It's something related to the production. Actually, we do not use a production, but we are going to use the gain instead of productions. But anyway, this transistor is something not only change the signal, but also it produces, amplifying the signals. So this element is going to be called active element. And for this active element transistors, before the solid state electronics, we used to have a vacuum tube, and probably you have learned about this vacuum tube functions in your high school or something. I don't think even in these days, even in a high school, they don't study on this vacuum tube, because everything is in solid state transistors, right? The same function can be done in this solid state using the semiconductor. Everything is in a solid state. In other words, in a vacuum tube, you have to have a vacuum tube encapsulated the 3 elements corresponding to the source and drains and gate. But in this solid state transistor, everything is inside the solid, so that in early stage, we used to have this discrete device. This discrete device is just here is a bipolar transistor, by the way, emitter-base collector, and then this is one piece of silicon, and it is encapsulated in some epoxy thing, and then it has a connections like this. So one transistor in one capsule, something like that, even though it is everything is in all solid state. But people find a way to make a connection of this each tiny transistors, discrete devices. Then we begin to have a microelectronic circuit era. Okay, so let's see. If you go further in this is actually the radio, size of the radio, and it says in a vacuum tube era, the minimum size, I think, is about 12 inch in length. Okay, and then when we have a semiconductor all solid state transistors, but we only can make discrete devices, then every transistor is connected on the board, something like this, which is B. Now it becomes 6 inch. We just can cut the size in half. That's all we can do. But after we find a way to make interconnections of these discrete devices in all one process, then the size of the radio becomes 0.1 inch. This is a remarkable reduction of the size. And with this interconnection technologies, now we can have personal computers. We can carry the computers. Okay, the computer size becomes very small. It becomes mobile, and this is a typical example of excuse me, large-scale MOS integrated circuits. Okay, and this is a particularly memory storage, which is going to be called the RAM, and it has about 35,000 transistors in there. And the total size is about 1 centimeter by 2 centimeter, that big. Okay, so that is what transistor integration is about. And then what we are going to do is, you can see in on this page, well, for the single crystal wafer preparation, it's going to be started from the sand. Okay, that is the silicon oxide basically. Okay, silicon dioxide, that is the sand, and then we make a reduction of that silicon oxide to silicon, and then with the special reactor we can purify that silicon up to 12.9. 12.9 means 9. The purity of that is 99.9999, and this is total number of 9 is 12. Very, very pure, right? And we know how to make that high purity silicon, okay? And then that high purity silicon is just a polycrystalline. In terms of the crystal structure, it is not a single crystal in any sense, okay? And then, since the polycrystal has so many defects, like grain boundaries and so forth, we want to eliminate those defects, and we have to do the wafer preparation. And the chapter 1 of this class is going to be the wafer preparation, the single crystal growing, okay? And then we call this ingot, okay? We grow the single crystal and then we cut it in the vertical sections, right, to make a wafers, which is shown like here, and then we just cut it to identify whether this silicon single crystal is N-type, P-type, or 111, or 100, or 110 directions, things like that, okay? And then to identify that, we make a mark, like one side flat, cut the one side flat, like this. That's why it is not circles. Anyway, and then we do all those 7 processes, unit process, to make all the wafers, the dies on the wafers, and then we cut it, and then we make a connection to the lead frame, and then encapsulate the plastic encapsulation. Packaging is going to be done. And we call this, at this stage, a chip, okay? So this class is basically related to the unit processes from the single crystals, and we have different mask. We had a lot of lithography thing, and making a thin film on top of the silicon wafer and an edge. Repetition of those things, we build up the transistors, okay? And then the function of the transistor is the same to the vacuum tube, okay? And we can make the transistor very micron-sized transistors through here. And then that is encapsulated the plastic packaging. So this all figures is related to that. Okay, before we go into the details of the unit processes, as an introduction, I want to mention about the yield issues. When we talk about the integration, in other words, we usually say this is 256 mega DRAM. Okay, that's popular in the industries. But before we can make 256 mega DRAMs, we start out with the 64K DRAMs. And then we just developed and improved the integration levels. So literally, it just have, how can I turn it off? Just turn it off? Do you think it's okay to use this blackboard? You forget it. I think you need a remote for that. Integration. When you talk about the integration, you start out with the 64K DRAMs, for example. And this 64K is, I think it's in the 1990s, early 1990s. We have 64K DRAMs, and it level up 1 mega, 4 mega, 16 mega, and 64 mega, 256 mega DRAMs. Now we are in the era of making 256 mega DRAMs. It just means that we increase the number of transistors to be collected in one place. And of course, we can improve this integration level by developing the techniques related to the each chapters of this class. But when we talk about the integration levels, we do not mention about the size of this integration. In other words, that we are not talking about the die size. So you may be curious that if you can make, for example, 1 mega DRAMs, then you put that thing together to make a 4 mega DRAM, and then the only thing you have to do is just to put them together, okay? So that 1 mega DRAM, if its size is 1 centimeter by 1 centimeter, then you make it 2 centimeter and 2 centimeters. Then it's going to be a 4 mega DRAM. Then why people say I can make a 1 megadram, but I cannot make a 4 megadram. Only you, the thing you have to do is just to put them together to make a 4 megadram. So it may be strange to you, but the reason why people say we have a technology for the 1 megadram, but we do not have technology for 4 megadram is related to the reliability issues. For example, if you have a wafer and that has been shown in the note, so I'll show you the note. Okay, let me see. Whatever. Okay. So this is one issue that if you make a wafer size big, why people want to make wafer size big? Because that if you have this small wafer, and then if you have this large wafer, and then if you have a same die size, okay, then in this case the dies on the edge, which is going to be wasted, okay, is a number of that die is 18. So the whole die 26, and then the percent on the edge is 41%. So 41% is going to be wasted. The die on the edges is not a regular die, so that you cannot make an integration on that die. So it's going to be wasted. But if you make a wafer size big, now it's the 29% is only 29% of the die is going to be wasted. So the production cost becomes very much cheaper if you have a bigger wafer size. That's why people want to make a wafer size big, okay? And then the yield is concerned. If you can make the die this small, and if you can make a die this small, then compare these two. You may say in your wafer the number of defects, 5 number of defects is inevitable. Okay, you cannot make defect-free, 100% defect-free wafers in the industries. So let's assume that the 5 number of defects is inevitable. You have to live with that. Then if you have a technology to make the die as small as like this, then the defects is number 5 and yield is going to be 96%. But if your die size is this big, then now the yield becomes 69%. Okay? In other words, if you have technology to make a 1 mega DRAM, but if you want to produce the 4 mega DRAM, then you have to increase the die size. Okay? And then in that case, the yield goes drastically goes down. So that in the real industry, it means that you cannot make it. The cost is too high. Production cost is too high. So one factory with that high yield, 96%, if he can make a 4 mega DRAMs with that 96% yield, and the other factory, he has a technology of 1 mega DRAM, but want to make a 4 mega DRAMs by collecting this 1 mega DRAM, the 4 of this, so that the die size increased like that, and then the yield goes down to 69%, and then the production cost is going to be very high. So that industry has a high production cost, and it is not the business is not going to go well because of the high production cost. Okay, so that's why people usually talking about the integration, they do not mention about the die size. It doesn't have, they don't have to say about the die size, because the die size is related to the yield, and a certain yield has to be guaranteed to make a production. So when we talk about we have a technology to make a 256 mega DRAMs, it means that we are not increasing the die size, but we just decreased the transistor size, okay? To miniaturize the transistor size so that in a certain specific area of the die, we can collect that much, 256 mega DRAMs in a regular die size. Okay, so that yield issue is very closely related to the VLSI technique. Okay. So the factors that is related to the yields are the wafer size that we had talked about. The dies on the edge of the wafer is going to be wasted, so we have to increase the wafer size. So wafer size is related to the yield, and die size, of course, as you have seen here, and the process number, how many processes has to be implemented to make a transistor. So the process, you have to simplify the processes to have a high yield, okay? The process number and the circuit density, defect density, of course. If you can reduce the defect density, then the yield becomes high. And finally, the crystal defect density, okay? Crystal defect density is related to single crystal growing. Okay, and these are the yield issues, and yield issues are very important. So whenever we talk about the unit processes, we have to make sure that that processes, how those processes is related to the yield, production yield, okay, things like that. Any questions? If you have any questions, please stop me during the lecture and then ask questions. And you can go, I think we cover up the page 24. And single crystal growing is the first chapter that we are going to discuss in the class. Okay, you guys know there's silicon has diamond cubic structures. Diamond cubic structures. silicon diamond cubic. And this is basically FCC, right? And then the atoms is going to be located like this, and then at the face center we have atoms there. So in FCC we have 4 atoms per cell, right? But in the diamond cubic structures, we also have in the diagonal, we are going to have one, two, three, 4 at the 4 quarter